Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it.
This is chapter 9.5, so chapter 9, section 5, which is alternating series. Right? So, first let's talk about what the alternating series test is. And it says the following. Let a sequence a sub n be greater than 0. The alternating series that is attached to that, so something like this, negative 1 to the n times a sub n, and negative 1 to the n plus 1 times a sub n. So either of these two kinds of series that are associated with the sequence a sub n, they converge. So converge when the two following conditions are met. The first condition is that the limit of the sequence is 0. So the sequence goes to 0, right? And the second condition is that it is a decreasing sequence. In other words, a sub n plus 1 is less than a sub n for all n. All right, so again, this just means that it is decreasing. So we need the limit of the sequence to go to 0, and we also need the sequence to be decreasing. If both of those two are met, then the alternating series is convergent. If they're not both met, then it would be divergent. All right, so let's look at some examples. Let's say I have the series from 1 to infinity of negative 1 to the n plus 1 over n plus 1. All right, now in here, well, what would the sequence here be? All right, notice here that when I define the sequence, I did not talk about that negative 1 to a power. So the sequence is essentially everything except that, the sequence associated here. Right, so in here, our sequence is 1 over n plus 1. And if we take the limit as n goes to infinity of 1 over n plus 1, that goes to 0. Good, so the first condition is met. But what about the second condition? Well, let's see. We need to have, so that's the first condition. The second condition is a sub n plus 1 actually less than a sub n? Well, let's see. What would a sub n plus 1 be? Well, that would mean that we're plugging in n plus 1 into our sequence. So I end up with, instead of n, I've got n plus 1 and n plus 1, right? Giving us 1 over n plus 2. All right, so is that definitely less than our sequence? Well, let's see. What we can do here is, let's consider the following. N plus 1 is definitely less than n plus 2, right? Irrelevant of what n is. In general, here we're talking about n being greater than or equal to 1, right? Because we're working with going from 1 to infinity on our series. But in general, n plus 1 is less than n plus 2. If I do a cross division here, I end up with 1 over n plus 2 is less than 1 over n plus 1. And look at that, 1 over n plus 2 is a sub n plus 1. And 1 over n plus 1 is a sub n. So it is definitely decreasing. So we have that the limit goes to 0. It is a decreasing sequence. So what we can say now, by alternating series test, our series from 1 to infinity of negative 1 to the n plus 1 over n plus 1 converges. All right. Next one, B. Let's say that we have the following series. We have the series of n over negative 2 to the n minus 1. All right, in here, the very first thing we need to look at, sorry, I meant to do n plus 1. the very first thing we need to look at here is, well, we need to have -1 to a power, right? Sorry, up here. -1 to n, or -1 to the n plus 1, right? So if we look at that here, how are we going to do this? Well, we can rewrite this series as the series from 1 to infinity of n over, well, -2 is the same thing as saying -1 times 2, right? And then we know from rules of exponents that that's -1 to the n plus 1 times 2 to the n plus 1. At that point, we say, well, dividing by -1 is the same thing as multiplying by -1. So what we really have here is the series from 1 to infinity of -1 to the n plus 1 times n over 2 to the n plus 1, right? And now that we have it in that format, now we can clearly see that this is an alternating series, right? We have -1 to a power of either n or n plus 1. So what we say now here is that our sequence is n over 2 to the n plus 1, right? Now, what we want to do here is take the limit of our sequence. So the limit as n goes to infinity of n over 2 to the n plus 1, right? By this point, you should be able to start recognizing this, that this actually goes to 0. Why does it go to 0? Because the bottom is an exponential. Exponentials in general increase faster than linear, right? So this overall thing should go to 0. Now, as far as actually showing why that would be true, well, what we can do is take the limit as x goes to infinity of x over 2 to the x plus 1, right? And we see, well, that goes to infinity over infinity, so what we can do is use L'Hopital's rule, and we end up with the limit as x goes to infinity of 1 over 2 to the x plus 1 times ln of 2. And as x goes to infinity, well, 2 to the infinity is infinity in the denominator, right? Infinity times ln of 2 is still infinity. 1 over infinity is 0. So we have that our sequence goes to 0. Now, the next thing that we need to check here is it a decreasing sequence? So the question is a sub n plus 1 less than or equal to a sub n, right? Well, let's look at this. Well, first, what is a sub n plus 1? Well, a sub n plus 1 would be, well, plugging in n plus 1 into a sub n, into our sequence, right? So what we have here is n plus 1 over 2 to the n plus 1 plus 1. What does that give us? That gives us n plus 1 over 2 to the n plus 2. All right? Now, the question is this actually going to be less than a sub n? Right? Well, let's consider the following. Right? In general, well, let's see. How are we going to write this? Let's write it this way. Let's consider that, well, 1/2 is, well, let's do it this way. I'm going to write it as, yeah, 1/2 is less than or equal to n over n plus 1 for n being greater than or equal to 1, right? But instead of looking at this as 1 over 2, that 1/2, what I'm going to do here is I'm going to multiply this 1/2 by 1. And the 1 I'm going to multiply by is going to be 2 to the n plus 1 over 2 to the n plus 1. Why am I using 2 to the n plus 1? The reason I'm using 2 to the n plus 1 is because I want to have something similar to here, that 2 to the n plus 1, right, of our sequence. And what happens when we do that? Well, this right side over here is still just n over n plus 1. If I do a kind of cross multiplication, if I move this up here and I move this down there, well, what do we get? I end up with n plus 1 over 2 times 2 to the n plus 1, that's 2 to the n plus 2. And that would be less than n over, move this down here, 2 to the n plus 1. And now look at that. 2 to the n plus 1 was our sequence a sub n. Excuse me, n over 2 to the n plus 1 was our sequence. And a sub n plus 1, that's this part over here. So what we found here is that a sub n plus 1 is less than or equal to a sub n. Good. So we had that the limit went to 0, It's a decreasing sequence, so that tells us that the series associated with that sequence, all right, of -1 times 2 to the n plus 1 times n over 2 to the n plus 1 converges. All right, it converges by alternating series. Next one, C. Let's say I had this series, the series from n equals 1 to infinity of -1 to the n plus 1 times n plus 1 over n. All right, this is definitely an alternating series because, well, we have -1 raised to either n or n plus 1, right? It would also work if it was n minus 1, but in general, we like to use n or n plus 1. Now, in here, what is our sequence? The sequence associated here with this series is just n plus 1 over n. And if I take the limit, that's supposed to say limit. If I take the limit as n goes to infinity of n plus 1 over n, well, I can multiply by 1, right? Anytime I want to, I can multiply by 1. And I'm going to multiply by 1 over n over 1 over n. What does that give me? That gives me the limit as n goes to infinity of 1 plus 1 over n over 1. I guess I could have also just split up this fraction. Doesn't matter. Either way here, 1 over n plus 1 over n goes to 0. So the limit is not 0. The limit is 1, right? 1 plus 0 over 1 is 1. So let's see what we found here. We found that the limit as n goes to infinity of a sub n, equals 1. But 1 is not 0. So it fails right away. Let me scroll up. It fails this first condition, right? That the limit of the sequence must go to 0. So right away, at this point, we can say that the series of -1 to the n times n plus 1 over n diverges, since the two conditions are not met. Notice we didn't even have to look at the second condition. Oh, as soon as it fails one condition, done, diverges. All right, cool. But again, it must be an alternating series. Next one. Let's say that I have the series from 1 to infinity of -1 to the n times e to the negative n. All right, well, let's see. What is our sequence here? Our sequence here is e to the negative n, right? That -1 to the n, that's just what makes it an alternating series. And in this sequence, if I take the limit as n goes to infinity of our sequence, I have e to the negative n. Well, let's write it this way. The limit as n goes to infinity of 1 over e to the n, that's 0, right? Because as n goes to infinity, e to the n also becomes infinity, so I have 1 over infinity, 0. Good. First condition is met. Let's check out the second condition. So if I have the limit as n, well, hold on, the second condition is not that. The second condition was a sub n plus 1 must be less than a sub n, right? That's the question. Is it a decreasing sequence? Well, let's figure out what a sub n plus 1 is. Well, in this case, it would be e to the negative n plus 1, right? I can rewrite this as 1 over e to the n plus 1. So now, let's consider this. This sequence of e to the negative n can be rewritten as 1 over e to the n, right? We know that already. So let's compare e to the n versus e to the n plus 1. Well, e to the n plus 1 is clearly the bigger one, right? For n being greater than 1, right? Because I'm raising it to a bigger power, right? E to the first is going to be smaller than e to the second. E to the fifth is going to be smaller than e to the sixth. So if I do like a cross division here thing, I end up with 1 over e to the n plus 1 being less than 1 over e to the n. And at that point, we say, well, This is just saying a sub n plus 1 is less than a sub n, which is what we wanted. It's a decreasing sequence. So what we now have is that the series associated with the sequence of negative 1 to the n from 1 to infinity of e to the negative n converges by alternating series, right? By the alternating series test, all right? Because it passed both conditions. It did go to 0 and it was decreasing. Now, let's talk about, well, now that we know that some of these converge, how can we estimate essentially what they converge to? All right, so approximately what value would they converge? Because what we're saying here is that they converge. So let's talk about this theorem. The theorem is called the alternating series remainder. All right, and let's see what this says. It says if a convergent alternating series satisfies the condition that it is decreasing, then the absolute value of the remainder and I'm going to call the remainder R sub n involved in approximating the sum S by the partial sum S sub n. So the absolute value of the remainder involved in approximating that is less than or equal to the first neglected term. All right. What am I saying here? What I'm saying here is if I take the actual sum and I subtract the partial sum, right? That difference, we're gonna call that difference the remainder, right? And that remainder is gonna be less than a sub n plus 1, where a sub n is, where a sub n plus 1 is the very first neglected term from our partial sum. So let's see how this helps us, right? So in here, this helps us figure out two things. One, using partial sums, we can sort of tell what the total sum should be, assuming that it is a convergent series, a convergent alternating series. And we can figure out approximately what the sum should be, right? So, for example, let's say approximate the sum of the series by its first 5 terms. All right, so what series am I talking about? I'm talking about the series from n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n factorial, right? Now, this is clearly an alternating series, right? Because we have negative 1 to n plus 1. Now, let's see. Is this a convergent alternating series? Well, what's our sequence here? Our sequence here is 1 over n factorial. And if I take the limit as n goes to infinity of 1 over n factorial, well, this bottom part is getting huge. So the overall fraction goes to 0. All right? So that first condition is met. Now is it decreasing? Well, let's find out. So this is the question, right? Is a sub n plus 1 less than a sub n? Well, let's see. What's a sub n plus 1? Well, a sub n plus 1 would be 1 over n plus 1 factorial. And the question that we're really asking here is, well, we want to compare 1 over n factorial over 1 over n plus 1 factorial. Well, in general, n factorial is less than n plus 1 factorial, right? Because in here, I'm essentially, well, let's do it this way. N plus 1 factorial is n plus 1 times n factorial. N plus 1 is definitely a positive value, right? Because n is a whole positive number. So n plus 1 is a positive value. And if I'm multiplying by a positive value, well, then n factorial will get bigger. And now if I do a cross division here, what does that give me? That gives me 1 over, I'm going to write it as just n plus 1 factorial is less than 1 over n factorial, which is what we wanted, right? Because it's what we wanted, because in here, 1 over n plus 1 factorial, that's our a sub n plus 1, and 1 over n factorial is our a sub n. So the second condition is met. So this is definitely a convergent alternating series. So this implies that this is convergent, right? Now that we know that it's definitely convergent, the question was to approximate the sum by its first 5 terms. So we need to figure out what S sub 5 is. And what that is, well, it's the partial sum of the first 5 terms. So that means, well, what does that give us? Recall that the series that we were talking about is 1 over n factorial with a negative 1 to the n plus 1. Perhaps I'll copy that. I'll put it down here. So this is something that we want to keep in mind. All right. So now, what is that going to give us? In here, if I just start plugging in terms, right? So plug in 1. If I plug in 1, I end up with negative 1 to the 1 plus 1, which is 2, times 1 over 1 factorial. 1 factorial is just 1, right? Plus negative 1 to the, well, now I'm plugging in 2. 2 plus 1 is 3, times 1 over 2 factorial. I'm going to write this as factorials. Plus negative 1 to the, well, this is the third term, so 3 plus 1 is 4, times 1 over 4 factorial, plus negative 1 to the fifth times 1 over 5 factorial, right? And what does that give us? Well, negative 1 to a positive, to an even power is positive 1. 1 factorial is just 1, so I have 1. Plus, negative 1 to an odd power is negative 1. And then 2 factorial is just 2, right? 2 times 1. The next one. Oh, I think I missed a term here, didn't I? So we're plugging in 3 here. So that should be 3 factorial. We're plugging in 4 here. So that should be 4 factorial. And the next one should be negative 1 to the 6 times 1 over 5 factorial. There, fixed. Good. All right, negative 1 to the 4th, that's a positive value. 3 factorial is 6. 3 times 2 times 1. Negative 1 to the 5th is negative 4 factorial. 4 times 3 times 2 times 1. So in other words, 6 times 4 is 24. Negative 1 to the 6th, positive value. 5 factorial is 120 because it's just 5 times 24. Right? In here, if I come up with a common denominator, well, the common denominator is going to be 120. Right? And what am I going to get here? Well, to go from 1, this is over 1. To go from 1 to 120, I must multiply by 120. To go from 2 to 120, I must multiply by 60. To go from 6 to 120, I must multiply by 20. To go from 24 to 120, I gotta multiply by 5. And then to go from 120 to 120, I just multiply by 1. And this gives me, well, 100 minus 60 plus 20 minus 5 plus 1 ends up being 76. Now 76 over 120, well, we'll just leave it as that. All right. Now, what have we found here? The remainder. Notice I'm using 6 here because I'm using the very next value, right? Actually, no, I should be using 5 there. The very next value is going to be for the other piece. So it's going to be the remainder for the first 5 terms is going to be equal to the total sum, right? S represents the entire sum. S represents this thing, that entire sum. So the actual sum there minus the partial sum is going to be less than or equal to the first neglected term, a sub 6. That's the first neglected term because I did the first 5 terms, right? 1, 2, 3, 4, 5. So the very first neglected term is a sub 6. And what is a sub 6? Well, that's going to be 1 over, well, let me write it this way. Negative 1 to the 7th times 1 over 1/20th, right? And in here, what we really want to do here is we want to consider the absolute value of this, right? Because well, let me put it this way. We're only looking at the sequence itself. The sequence is just without that alternating stuff, right? So a sub 6 is just 1 over 1/20. So what we're saying here is that our remainder is going to be, well, the total sum. So our remainder, let's do it this way. This gives us that the total sum, the absolute value of the total sum minus s of 5. That's the partial sum of the first 5 terms. That's 76 over 1/20. That's going to be less than or equal to a sub 6, so it's 1 over 1/20. This absolute value inequality, we can rewrite it as this. Negative 1 over 1/20 is less than or equal to s minus 76 over 1/20 is less than or equal to 1 over 1/20. If I solve for s, in other words, I want to move this negative 76 over 1/20 out to both sides of this inequality, I end up with, well, 75 over 1/20. Oh, hold on. Oh, look at this mistake. This is not 1/20. 6 factorial is 7/20. This should be 1 over 7/20. What an awful mistake I just made. That's okay. That's an easy one to fix. 7/20, 7/20, 7/20. All right. Now, let's go back to what I was saying here. If I add 76 over 1/20 to both sides here, what do I end up with? I end up with, well, I'm just going to go ahead and give you the reduced fractions. We end up with 91 over 144 is less than or equal to s. It's less than or equal to 76 over 1/20 plus 1 over 7/20 is 457 over 7/20. So what do we find here? Well, what we found here, well, 91 over 144 is 0.63194 with 4 repeating. And then 457 over 7/20 is 0.63472 with 2 repeating. So in here, what did we actually find? Well, we found a good approximation of what this total sum is, right? This entire sum for this series. And what does it give us? Well, somewhere between these two values, all right? And our remainder, right? Our remainder was essentially less than 1/7/20th, right? From here, it's less than 1/7/20th. All right, now let's do something let's do a problem that's tangentially related to something like this. Determine the number of terms required to approximate the sum of the series with an error less than 0.001. All right. So essentially, what we're saying is we want to figure out how many terms we would need so that our partial sum is within 1/1000th. Right. That's 1/1000th is within 1/1000th of the actual value. All right. So how many terms would we need to figure that out? Well, what we're gonna do here is we're gonna consider what we wrote up here. And I want to do this here. Where is it? We're gonna consider this, and essentially just this piece right here. All right. So let's look at that, and maybe I'll just copy and paste this so that we can keep it in mind. And there we go. So we're gonna use this. We're gonna use this idea of the remainder here to try to figure out how many terms we need. All right. So essentially, what we're saying here is we want our remainder to be less than 1/1000th. Right. That's 1/1000th. So how do we do that? So what we're gonna say here is we're gonna force this to be less than. Well, let's do this. I want to talk about this being 1/1000 first. All right, cool. That was exciting. Oh, I should probably give what series we need here. Uh, that was awful. Let's give the series that I'm talking about in this problem. The series from n equals 1 to infinity of -1 to the n plus 1 over n cubed. All right. Notice that this is definitely a converging alternating series. All right. We have 1 over n cubed. The limit of that goes to infinity. We also have that is a decreasing sequence, right? 1 over n cubed. Well, maybe I'll prove that. So in here, a sub n is equal to 1 over n cubed. The limit as n goes to infinity of 1 over n cubed goes to 0. Good. A sub n plus 1 would be 1 over n plus 1 cubed. And clearly here, well, if I start with n cubed, well, let's start with n. N is clearly less than n plus 1, which tells us that n cubed is definitely less than n plus 1 cubed, which if I do a cross division here, this gives me now that 1 over n plus 1 cubed is less than 1 over n cubed, which is good. So we have that the limit goes to 0, the limit of the sequence goes to 0, and the sequence itself is a decreasing sequence. Good. So we know that it's convergent, right? Good. But now that it's convergent, we want to figure out how many terms we would need to be within 1/1000th of the actual value. So again, I'm going to go back to this idea here. That remainder, which is less than a sub n plus 1, right? So let's see what that gives us. So I'm going to talk about the remainder. We want that to be less than or equal to a sub n plus 1. But what is a sub n plus 1? A sub n plus 1 is 1 over n plus 1 cubed, right? We just found that here. And, well, how do we force the remainder, which is less than a sub n plus 1? How do we force that to be less than 1/1000? Well, what we can do here is, well, ignore this side and force this to be less than 1 over 1000, right? So that would definitely make our remainder be less than 1/1000 if I make it less than this term. So what does that give us? Well, in here, 1000 is the same thing as saying 10 cubed, right? And if I do a cross multiplication here, that gives me that 10 cubed is less than n plus 1 cubed, which now tells me that 10 is less than n plus 1, right? And if I rewrite this, well, this is really saying n plus 1 is greater than 10. If I move the 1 over, n has to be greater than 9, right? So what did we find here? What we found here is that we would need at least 9 terms, right? So this tells us we will need, let's write it as we, or just need more than 9 terms to ensure Ooh, that's a weird. To ensure that our partial sum S sub n is within 1/1000th of the total sum S. All right, now these two last examples, where we spoke about finding the remainder and figuring out how many terms we would need, I would not recommend you focus too much on these kinds of problems. All right, they do come up in general, um, but I would rather you focus in the other stuff about alternating series. In other words, what we spoke about before this, in the first three problems. Now, and also about in I also want you to focus into what we're going to talk about next. So, absolute and conditional convergence. All right. So sometimes, um, we have series. We have a series that has positive and negative terms, right? But it is not an alternating series. So what do we mean? So let's consider the following. Consider that I had the series from 1 to infinity of sine of n pi over 2 over n squared, all right? And let's see what our terms are. If I plug into 1, so I have sine of pi over 2. Sine of pi over 2 is 1 over. If I plug in 1 down here, 1 squared is 1. So that was the first term. Plus the next term, plug in 2. Sine of 2 over 2. Ooh, I didn't actually want to do pi over 2. I wanted to do pi over 3. So let's fix that before I get too much further in here. There we go. N pi over 3. Cool. Much better. So let's plug in 1. Sine of pi over 3. Sine of pi over 3 is radical 3 over 2. And we have that over 1 squared. Plus the next term, plug in 2. 2 pi over 3. Sine of 2 pi over 3 is radical 3 over 2 as well. But now we have 2 squared, so that's 4. Plus, plug in 3. Sine of 3 pi over 3. Sine of 3 pi over 3, well, that's just sine of pi. So that gives me 0 over 3 squared, which is 9. Plus, that was the first three terms. Fourth term, sine of 4 pi over 3. Sine of 4 pi over 3 is negative radical 3 over 2. And now we have 4 squared, which is 16. Notice we have a negative now. So that's the fourth term. Fifth term. So sine of 5 pi over 3. Sine of 5 pi over 3 is negative radical 3 over 2. And we have this over 25. Let's do the sixth term. Plus sine of 6 pi over 3. 6 pi over 3 is 2 pi. Sine of 2 pi is the same thing as saying sine of 0, which is just 0. And then 6 squared is 36. So on and so forth. Well, what I want you to notice here is what pattern is happening here. We end up with a positive, positive, 0, negative, negative, 0 again. And, well, the thing about sine is that it ends up repeating itself over and over again, right? It's circular values there. So it's going to be, again, positive, positive, 0, negative, negative, 0, positive, positive, 0, so on and so forth, right? The idea here is that we have positive terms, we have negative terms. We also happen to have some 0 terms, but those 0 terms are inconsequential here. The idea is that we've got positive and negative terms, but this is not an alternating series. It's not an alternating series because it's not going from positive to negative to positive to negative to positive to negative, so on and forever. All right, so on and so forth. But that doesn't mean that we can't figure out what this is doing. All right, so let's consider the following. So how do we figure out what this is doing? So consider the series of the absolute value of sine of n pi over 3 over n squared. All right, and let's think about this. Well, in general, sine is between -1 and 1. That's sine theta. But what's my theta here? N pi over 3. So I really have that 1 is less than sine of n pi over 3, which is less than 1. And in here, well, I don't really have sine of n pi over 3. I have over n squared, right? Well, actually, before I do that, because I'm working with the absolute value, I'm going to write this as absolute value of sine of n pi over 3 is less than 1. It's between 0 and 1. It could be 0. So I'll put it as less than or equal to 0. Okay, cool. 0 is less than or equal to that. There we go. I said it wrong. But anyway, now in here, we're going to ignore this side, but we're going to divide both of these by n squared. So I have sine of n pi over 3 divided by n squared. That's going to be less than 1 over n squared. All right. And now what this really tells us is that this series from 1 to infinity of the absolute value of sine of n pi over 3 over n squared is less than or equal to the series of 1 over n squared. But we know what this series does. This is a p-series, right? So in here, since the series from 1 to infinity of 1 over n squared converges by p-series, then this one over here, the series from n equals 1 to infinity of sine of n pi over 3 over n squared, also converges, but this time by direct comparison. By the direct comparison test. All right. So we were able to find that the absolute value of this converges. Now, how does that help us for the original series that I was talking about? Right, this one was an alternate. It wasn't alternating, but it behaved sort of like an alternating. Well, that's where this next theorem comes in. All right, so let's talk about this theorem. The theorem is called absolute convergence, and this is what it says: if the series of the absolute value of a sub n converges, then the series without the absolute value of that sequence also converges. All right. If the absolute value version converges, the non-absolute value version also converges. All right. Another way of saying this, and I'll write this perhaps in blue. This is also saying if the series without the absolute value of n diverges, then the series with the absolute value of n also diverges. Right? What this is not saying, so it is not saying that if the non-absolute value converges, then the absolute value also converges. All right, it is definitely not saying that. This is a false statement in general. So now, before I continue, in here, we find that the absolute value version converged. So this, by this theorem, would imply, and perhaps I'll do that in different color, like yellow. So this would imply now that the series that we were originally worried about without the absolute value, so sine of n pi over 3 over n squared, converges, right? Because we found that the absolute value converged, so the non-absolute value must also converge. That was this theorem. Now, let's look at why this statement um, is a false statement. So why is it that if a series converges, then we can't say that the absolute value version also converges? Well, consider um, consider this series: -1 to the n plus 1 over n. Right now, this is a convert. I mean, excuse me. This is an alternating series, right? Because we have -1 to the n plus 1. Now, let's see. What is our sequence here? Our sequence is 1 over n. And if I take the limit as n goes to infinity of 1 over n, that goes to 0. Good. Now, is it a decreasing sequence? Well, the question here is a sub n plus 1 less than or equal to a sub n? Well, what's a sub n plus 1? A sub n plus 1 is equal to 1 over n plus 1. So at this point, we're going to say, well, we know that n is less than n plus 1 for n being greater than or equal to 1, which implies now if I do a cross division here that 1 over n plus 1 is less than 1 over n, which is good because this is showing that a sub n plus 1 is less than a sub n. Good. So what did we find here? We found here that the series from 1 to infinity of -1 to the n plus 1 over n converges by the alternating series test. But now, let's look at, however, let's look at the absolute value version of this. The absolute value version of this would be the series from 1 to infinity of 1 over n. This right here, this is a p-series with p equals 1. Or you can think of this as, this is the harmonic series. And the thing about the harmonic series is that it diverges. So this is divergent. All right? And I guess I could say divergent by p-series, where p is equal to 1. All right? So what did we find here? We found that the alternating series converged, but the absolute value version diverged. All right. So in general, you cannot just say that if a series converges, then the absolute value version would also converge. All right. This is a good counterexample to that. This leads us to our next definition. Whenever we have a scenario like this, where the regular series converged but the absolute value version diverged, then we can talk about something called conditional convergence. So definition. So absolute and conditional convergence. All right. So the scenario that we just spoke about. So if this, I mean, not this first scenario, the definition that I already gave up here. This absolute convergence. All right. That's that thing. So if the series from 1 to infinity of the absolute value of n, of the absolute value of a sub n, excuse me, converges, then that series of a sub n from 1 to infinity is said to be absolutely convergent. Right? It's said to be absolutely convergent because the absolute value version converge. But not just that, we know that if the absolute value version converges, then the non-absolute value also converges. 2. If the series of a sub n, so the non-absolute value, if the non-absolute value version converges, but the absolute value version diverges, we say that, so we say that in general, the series of a sub n is conditionally convergent. All right. So there we go. Let's do an example here. So again, if the absolute value converges, we already know that the non-absolute value also converges, and that tells us that it is absolutely convergent. If the absolute value, if the non-absolute value converges, but the absolute value version diverges, then it is conditionally convergent. All right. So either way here, we need to figure out what the absolute value version thing is doing, right? So we gotta figure out, well, is it diverging or is it converging? The absolute value version. All right. So now let's look at some examples here. Let's look at the series from 1 to infinity of -1 to the n times n factorial over 2 to the n. All right. Now this is an alternating series, clearly, right? We have -1 to the n. But in here, if let's take a look at this series overall. What is our sequence? Our sequence is n factorial over 2 to the n. We have a factorial over an exponential. In here, you should recall now that the limit as n goes to infinity of a factorial over an exponential does not go to 0. All right, remember that n factorial grows way faster than an exponential. So that doesn't go to 0. So that tells us right away that this is divergent. But that was a non-absolute value one, right? And with the non-absolute value, that wasn't anything to do with this. So right away, we can't say anything about this being conditionally or absolutely convergent because the non-absolute value was divergent. All right, right? It failed the very first thing for the alternating series test. Now, let's look at the sum from 1 to infinity of -1 to the n over square root of n, right? This is an alternating series. It's alternating because we have -1 to the n, right? Now, does this alternating series converge or diverge? Well, let's do this. So what's our sequence? Our sequence is 1 over the square root of n, right? N to the 1/2. And if I take the limit as n goes to infinity of 1 over n to the 1/2, that's 0. Good. So far it's looking good for our alternating series test. Now, what is a sub n plus 1 doing? Well, a sub n plus 1 would be 1 over the square root of n plus 1. And in general, well, we know that n is less than n plus 1. So the square root of n would be less than the square root of n plus 1. So if I do a cross division here, 1 over the square root of n plus 1 would be less than 1 over the square root of n, which is good because this is giving us that 1 over n plus 1 is less than a sub n plus 1 is less than a sub n. Good. So we know now by alternating series test that the series that we cared about, -1 to the n over radical n, is convergent. But the question is this absolutely convergent or is it conditionally convergent? All right, so let's figure that out. So how are we going to do that? What we're going to do is, well, consider the absolute version of this, of -1 to the n over the square root of n. Well, the absolute version of this is just the series from 1 to infinity of 1 over n to the 1/2, which is divergent by p series, with p being equal to 1/2, right? We know that when p is between 0 and 1, this p series, it is divergent, So what do we have here? We have that the absolute value version diverged, but the non-absolute value version converged, right? And by our definition here, absolute value converged, non-absolute version, non-absolute version converged, and absolute value version diverged. We have a conditionally convergent series. So in here, we say that the series is conditionally convergent. All right. Let's do another one. And actually, before we do another one, let's think about this a little bit more. And I want to talk about these definitions again. Either way, again, we need to look at the absolute value version. So since we need to look at the absolute value version, in general, we can already just go ahead and start with that. All right, we can go ahead and start with that with the absolute value version. You'll see what I mean in a second. So example H. Let's say that I had the series of -1 to the n times n plus 1 over 2 over 3 to the n. Now this seems like it would be an alternating series because we have -1 to a power. But let me give you the first couple of terms here. This is -1/3 minus 1/9 plus 1/27 plus 1 over 81 minus 1 over 243 minus, and that was a 243, minus 1 over 729 plus so on and so forth. So this is not alternating because we have negative, negative, positive, positive, negative, negative. We're going to have positive, positive again. So it's not alternating at every single term. So that makes this not an alternating series. So because it's not an alternating series, we can't even apply the alternating series test. But what we can do is consider the absolute value version of this. The absolute value version of -1 to the n times n plus 1 over 2 over 3 to the n. And this the absolute value version of this, well, what does that give me? That gives me the series from 0 to infinity of 1 over 3 to the n, right? Because that -1 absolute value just becomes 1. And in here, this is geometric, right? It's geometric with r being equal to 1/3. And the good thing about that is that 1/3 is less than 1. So now that tells us that this series is convergent by geometric series. And look at that. The absolute value version was convergent. Now that I know that the absolute value is convergent, I don't even need to worry about the non-absolute value because right away that's going to tell me that that the series is absolutely convergent. The only scenario where I would need to like figure out what this series is doing is if I had gotten that it's divergent, right? If it's divergent, if the absolute value version is divergent, okay, then we need to look at what the non-absolute value version is doing. But if right away I see that the absolute value version is convergent, done. It is absolutely convergent. All right. Let's look at another one. So that was H. I. So let's look at the series from -1 to n of ln of n. And we're going from 1 to infinity. Sorry, we can't go from 1 to infinity because 1 would make this 0 on the bottom. We technically have to start at 2. But the idea will remain the same. Right? It's just one less term. Now, I'm going to look at the absolute value version right away. The absolute value version of -1 to the n over ln of n. And if I look at this absolute value version, what is that saying? That's saying the series from 2 to infinity of 1 over ln of n, right? And in here, well, what is this doing? Well, let's see. Our sequence here, a sub n, is 1 over ln of n. right? Now, this is actually going to 0. So if I take the limit as n goes to infinity, 1 over ln of n, that goes to 0. But the fact that it goes to 0 is kind of useless here, because this is not an alternating series anymore, right? This is no longer alternating, so we can't use the alternating series test. And even if we try to do the test for the nth term test for divergence, well, recall that when it goes to 0, it tells us absolutely nothing, right? It's only when it doesn't go to 0 that we know that it would be divergent. So what can we do here? Well, let's consider the following. Consider that n in general is greater than ln of n for n being greater than 2. Right? I should say greater than or equal to 2. And you could try plugging in some values on there, but you would see that linear grows faster than logarithmic, right? So from there, if I do the cross division, I end up with 1 over ln of n is greater than 1 over n, which is great because now I have this comparison of these two series, right? And again, we're going from 2 to infinity, right? And the thing about this one over here is that this is the harmonic series, right? This right here is divergent. Well, we could say harmonic series or the P series. Either way, it is divergent. And this one over here is bigger than a diverging series. So by direct comparison, this series of 1 over ln of n diverges. All right, well, I mean, that's good. That's good that we finally know what that's doing. But the question is this, the question was it conditionally convergent or absolutely convergent? Well, we don't even know if it's any kind of convergent. All we know that so far is that the absolute value version diverges. So now that we have that, I actually do need to figure out what the non-absolute value version was doing. So the series of what was it, negative 1 to the n, right, over ln of n. Well, what is this doing? Well, if I take my sequence here, a sub n, that's 1 over ln of n. If I take the limit of my sequence, 1 over ln of n, well, as n goes to infinity, ln of n goes to infinity, and 1 over infinity goes to 0. Good. And now, let's see, is this a decreasing sequence? Right? So, let's see what happens here. What's a sub n plus 1? A sub n plus 1 would be ln of n plus, 1 over ln of n plus 1. Now let's compare that with our series. Well, let's see. We know that n is definitely less than n plus 1. So ln of n is less than ln of n plus 1, right? If you think about ln, normally it looks like that, right? So it starts getting bigger and bigger like that. And if I do a cross division, I end up with 1 over ln of n plus 1 is less than 1 over ln of n, which is good. Why is that good? Because that's telling us now that a sub n plus 1 is less than a sub n. And now we've got that the limit went to 0, and it is a decreasing sequence, which implies that this series that we cared about of negative 1 to the n over ln of n is convergent by alternating series test. So what do we find? We found that the non-absolute value version is convergent, but that the absolute value version that we did over here was divergent. So what this tells us now is that this is conditionally convergent. So overall, that series from n equals 2 to infinity. Well, let's write it this way. I'm going to write it as, since the series of -1 to the n of a sub n is convergent, and the series of just the absolute value version of that, right? I write it this way, is divergent. This implies, or I can say we know, that the series, I'm just going to write it as the series, is conditionally convergent. All right. All right. That is the end of 9.5. All right. But again, in here we had, well, the alternating series test, and along with the alternating series stuff, you should always be checking whether it's absolutely, but like if you end up with a convergent series, you should check if it's absolutely convergent or conditionally convergent. All right.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.